OK。Start? ザビラさん、can you start first? I cannot hear your voice. No, I cannot hear.
Hello?
Small voice.
Small voice.
Okay. Now it's okay.
Okay.
Yeah.
We take a look at the optimize this one, the one that I've been trying, optimize design. So this week I did what you asked to do. So we try to put viscoelastic and metallic damper on the top, 10 for and here 7, 6, and then the bottom one is the only metallic damper, or we also can put and this is the response. So if you can see, so I have 4 trials inside. So this is first trial, try 1, the orange. So when we have a metallic beam at the bottom and viscoelastic at the top, the bottom have asymmetry, and the gray color is the S beam. From the bottom until the top story is steel beam, and the green one is optimized. Only in the middle one have a viscoelastic and metallic damper. And this is the acceleration. And then I also we put the top as metallic damper and bottom viscoelastic plus metallic damper. And the if you see the orange color, the story drift doesn't change in worse actually. And then the third trial, so we put viscoelastic, the damper on top and bottom, and the middle is damper, and it also reduces a bit, but it doesn't. Is already over the limit of the drift, the orange color. And try number 4. So what I did is I same position. The middle one, we put damper, and the top story 1 damper on the 10th floor. And I also improved the wall. The bottom wall, I increased the size. So the orange color actually have a bit performance better than the optimized one. And then this the other option that we can do is to reduce the acceleration. We can increase the size of the wall at the bottom. And then I also try. So we start at the first beginning of the experiment with the steel beam to see the story drift. The first trial that we use is the size is 600 by 200 for steel beam, and this is also the temper. So I compare what if we use 10%, 50%, and 20%, and this is the story drift. I also
you change what? What is the percentage? 100?
The damp and viscoelastic damper.
Which damper you change percentage?
From this, the metallic and also viscoelastic together. Let me open the properties for you. So here, the thing. This is for viscoelastic, and this one for metallic. So we have 10%, and 60, 40, and 20, also similar as viscoelastic. And then I apply here. This one should be this one. The 50 should be 60. And then I also
60 means you reduce the strength of metallic
Yes, and also viscoelastic. Yes.
You change both.
Both, sensei.
Same ratio.
Yes, and this one, the middle one, I changed. You asked me to compare if I take. What if we take like 60% metallic and 100% viscoelastic, and this one I the damper percentage. So metallic 20% and viscoelastic 60%. Like lower the metallic damper.
Which line is which one?
The red one. The red one here.
Both red one.
No.
No.
Another one is pink.
Pink? I cannot recognize.
Can you see?
It looks same color.
Okay. I will open the yes. Okay, I changed this one. And then okay. Can you see something? So the red one, 60% of metallic and 100% viscoelastic. The green one is 20% metallic and 60% viscoelastic. So
why you reduce both?
Why I reduce both?
Yeah.
I have to maintain 100% viscoelastic and only change the metallic.
Yeah. Why you reduce both? And in case of 60 metallic and 100% viscoelastic, is metallic damper yielding or elastic range?
Yes. I think it's still, can I try here? Let me open the coin. So the viscoelastic is V1. This is level 3.
The same damper along the height.
Same damper along the height.
And
we try.
Damper is elastic. So metallic damper is not working actually.
I think if most of the cases, if I put along the height, the same damper, the metallic.
So I suggested to reduce the strength of metallic damper.
But this 40%. I can reduce 20% if you want to check. So 100 or 20%. This is 20%.
No, it's metallic damper is working. Yeah. So this is what I want to ask you to do. So metallic damper is working like limits of the force. Yeah, it's a fuse function. So Zafira-san were changing location of damper. I mean, upper part is metallic and the middle part is viscoelastic. Interesting, but how to say? How do you find the optimum distribution?
There's a previous paper that is like this. They only put the viscoelastic at the middle. So remember this one? This is the building from internet. So I try to apply the same method. And
but the other story is that
it's I think it's concrete beam. It's not damper. It's no coupling beam.
Ordinary beam.
Yes, I see.
Okay.
And I also, so I was thinking if we just apply that, we also can reduce the cost for the constructions. And I also try, this is, I reviewed the beam size. So we use 600 by 200, and this one I increased the steel beam size from 700 to 750 times 50. And this is steel beam along the height, and this is the story drift and the accelerations. And after I optimized the steel beam for 750 is much more better than 600, and also acceleration is like around 800. It's only at level 5, 6, and 7. And this is deformation for the metallic damper and viscoelastic.
But if you increase the steel size, it costs money, right?
Yes.
So, well, how to say? You need some theory. Like, if you want to discuss about optimization, you objective function.
It's like the how much energy dissipation from the.
Yeah. This is the response, but also the amount you reduce the cost.
Right.
But
yes,
it's not so easy to find optimum distribution.
So we stick as the previous, so damper along the height.
Yeah.
But if I apply this method like 20% metallic and 80% viscoelastic, I might not sure if we can reduce the story drift. Like this, the story drift is might not be reduced.
But in this case, you reduce both viscoelastic and metallic, both you reduce together.
But this one, I use 20% metallic and 60% viscoelastic.
Are you sure metallic is yielding?
For this one?
Yeah. At least 60% and 100%, no, metallic damper is not working. It's elastic, right?
Okay.
And 20% viscoelastic. Did you check if metallic damper is yielding?
Fine. 80%, so I reduced to 8.55. So this is 60%.
No, metallic damper is not yielding.
But this one is 20. Yeah, okay. So I will check for 20% and 80%. The storage.
Oh. Yeah, before you start analyze, please make a story of your paper.
Okay.
Okay, you have a viscoelastic damper. First, you have a two shear walls, coupling walls.
Okay.
Yeah, and you agree. Yeah?
Yes.
So don't change the size of wall. Okay, you fix
Okay.
the wall,
Yes.
and starting from steel beam only.
Okay. Yes.
And first, you try to increase the size of steel beam so that the story drift satisfy the optimum value. Can I change? Can I draw?
Yes, yes, yes. Yes, yes.
No. Yeah, you made many analysis, but I cannot see the story. So let's see. Can you see my handwriting?
Yes, yes, yes.
Okay, two shear walls and coupling beam. You must check if no coupling beam, just two individual walls, and you input the design earthquake, story drift. It must be more than target drift, 1/250. Yeah. So this is a starting point.
Yes.
Now you try to find a design. Okay. So number one is ordinary coupling beam, no damper. Put no damper. So in this case, this is reinforced concrete or steel?
We can use if we use steel. Previously we used steel instead. But when we use steel, our drift is less than the limit, so we take the percentage damper from the steel beam. So we have concrete or steel.
Usually reinforced concrete beam is I think it's most popular.
Mhm.
And but you must be careful about shear failure.
Mm.
Shear failure. So, I don't know. なんていうかな。So, not good.
Okay.
Not good. So how to tell not good? Maybe that, maybe, I don't know,
Okay.
too much damage or too much. I don't know, drift is over than 150, 250. Have you done before? Only reinforced concrete beam.
I think last time we start with metallic beam.
Oh, you haven't tried reinforced concrete beam yet.
Not yet, she said.
Not yet.
I think the early years we tried RCB. After that we focus on metallic and damper. I think last time she said the size also is 600 times 300 or 200 mm. The size of RCB.
Okay, so let's skip this now. Number 2. じゃあ、これナンバー2、これやめるか。いいかな。Okay, so let's, if we have time, we can try.
Okay.
But, we skip this one. Number 3. Steel beam. Maybe metallic damper only.
Okay.
Then, and you start from 1% and reducing up to, I don't know, what is that?
20%.
20% is the smallest, right?
Yes.
You can find the optimum percentage. Optimum percentage. Yeah? So this is number 3.
Okay.
4. Only big damper.
Okay.
You also select 100% to 20%.
Yes.
Then, and I don't know if you have optimum or not. Do you have optimum percentage also?
It's around 60.
Okay, so you have optimum percentage. But in this case, I remember is very large. I remember. You satisfy drift with criteria.
I think, Sensei, that is the location that I optimized. The one that we discussed previous week, that the drift is less than the limit, but there's a little bit more. That one is we optimize the locations.
No. I'm talking same dumper along the height.
Okay.
I think you have done before.
Okay.
And also this is same dumper along the height you have done before. And number 5, viscoelastic plus metallic combination. So in this case, viscoelastic damper, if you say 60% is the optimum, you keep it, not to change.
Okay.
And only change metallic damper, but it must start to yield. So every time you must check the hysteresis. And so find out which percent is best. Do you know how much percent for metallic damper optimum?
Last time was 75 is the best.
75%?
Yes. So it's around 60 to 80%.
75%. Okay. So I hope you can find viscoelastic plus maybe metallic is not 75%. If you combine viscoelastic, maybe only 30%.
Okay.
I mean, the advantage is if you can reduce percentage, it means you can reduce amount of metal.
Okay.
And the viscoelastic, if you say 60%, is if you use only viscoelastic, 60% is optimum.
Okay.
But if you combine metallic damper, you can say.
Okay.
So the best answer is to use more. If you combine two dampers, if you can reduce more compared to same damper along the height.
Okay,
Same damper along the height, both percentage is 70% for metallic damper alone, 60% for viscoelastic damper alone. But if you combine two dampers, you can reduce both. So this is the answer, in my opinion. Then you can discuss. If you want to discuss more, you can discuss arrangement of damper.
Okay. And after that, displacement design method. The final one.
Can you do this week and maybe
Yes, I can do it today.
today? Yeah, you analyze quickly, but you must. えっと、I think you should make a plan
Okay.
before story. Yeah. And if you want to optimize the distribution, you need some theory how to
Understand.
optimize. And what is the objective function? Not only story, maybe.
Maybe the optimized location we can do for other paper. So this one we focus on the tempo only.
Yeah, but in my opinion,
Yes.
after you finish this one,
Mhm.
but actually nothing discuss about the distribution. So you put the same damper along the height,
Yes.
okay, and your study is fine, two dampers.
Oh,
That's
yes.
all.
Yes.
Yeah, and then my interest is how to obtain the result by displacement-based design. I mean, without using ties, we have our design spectrum, and we must calculate equivalent damping for viscoelastic material, equivalent damping for metallic damper, and if you combine two dampers, and you add two equivalent damping factor, or previously we proposed to have a damper of viscoelastic square, damper of hysteresis metallic damper square, and taking root. And this could be total damping. So this is our proposal. I want to know if it works or not.
Okay.
Okay.
The equivalent damping that we calculate from this study sensei, actually we use the energy.
Yes,
Yeah.
yes. Yes.
I think I can compare.
And this hysteresis damper is a bilinear.
Mhm.
So there is a formula. You remember?
Yes, I remember. You gave it to me.
And
One. No.
viscoelastic. So also there is a formula.
Yes.
Did we discuss before?
Actually, I have found from the previous research. So, example.
Yeah. I think that, yes. Yeah. And yeah, so this is we must be careful how to obtain HV.
Okay.
Okay, so you obtain, maybe you can do calculate analysis, yeah, quickly,
Okay,
but please show me.
Sorry, I will make slide for you so you can see properly the result. Okay. Then I also searched some catalog about this is for you asking me about the material property. This is from Japan. This is one damping. This is a paper from Kohei-san and Hideyuki-san. So the title of damping performance evaluation test of viscoelastic damper using
Which
Harper Fox.
company they are working for?
Let me open the. But it's in Japanese.
Mhm.
Can you see? Okay. Like this.
Could you go down?
Now?
Yeah. 株式会社関東学院大学。I don't know. Constic company. Constic. I've never heard. Constic. Oh, okay. Can I share my screen? I can
Yes,
show
yes.
you
Right.
the website. So this is the website of Constic. And yeah, they are doing some seismic retrofitting. Under damper, yeah, VES damper. They put the damper not in the beam, inside the column. Why it's possible? Column is supporting axial load. So why it's possible? Okay. They said that it's I mean, how to say, there is an actual column both sides, and the middle part, it is like a column shape damper. It cannot support any actual force.
Okay.
Okay. Really? But it's not a big company. How many people working there? Yeah, small. Okay. Not so many people. But okay. Very good. Small, but they are developing
Ambitious.
technology. Okay. Yeah.
And then this second one show it for. This also is like more application to the wall.
This is Sumitomo Riko.
Sumitomo Riko. And this one is from Nippon Steel Engineering. Also, they apply for, I think, column. Same like the previous company, the first one.
But it looks like a wall.
Wall?
Yeah. The size is very wide. Yeah. And any difference in the parameter? What is C value is here? Damping coefficient.
Only this is shear force, maximum shear force. And this one is one about size, explaining about size. But in this paper, they also talk about the equivalent shear modulus and viscous damping factor. But maybe because this is from paper, so they discuss more details. But in the catalog, they just mention about the properties, the size, and how much capacity it can take. Okay. And from overseas, out of Japan, mostly I found it from paper. So this paper, the properties, and this is how the viscoelastic damper looks like. And this paper actually took the properties from Chang here, this researcher. And this researcher used this formula to evaluate the properties. So same researcher I use for my application for viscoelastic. So this is from the Christopoulos book. From Christopoulos book, he also took from Chang in 1993. This one, and this is the paper of him, and it's a steel frame. So basically, we have three different type of viscoelastic material, and they use this is the different equation to define the stiffness of the viscoelastic. And they also did some frequency tests for
So
the
3 ABC is just the area and the thickness.
no, the stiffness of the material is different. If you can say they have different coefficient.
Yeah,
Yes.
but
Yeah.
table 2
Table 2,
size is different.
the size also different.
How about the rubber itself? Is it same rubber?
Different rubbers in same.
Are you sure?
Yes.
Why?
Because in the paper we opened Christopoulos book, they also have different.
So if you use different rubber, how is the gradient is different?
I believe the stiffness properties is different.
No. I'm asking material.
Material.
Stiffness is different because the size is different, right?
Mm-hmm.
Material might be same
Okay.
rubber, but I believe they took same material size.
This one. They have different hysteresis.
Could you find out about the material, plastic material?
Okay, Sensei.
What kind of material they are using?
They use. Okay. Okay, Sensei.
Could you find now? No?
No? Okay.
Geometry.
This one of the stress tests that Chang did, evaluate dynamic cyclic shear response of three different types of viscoelastic material. The configuration of the damper test was similar to figure 6.4. And then these three damper type of viscoelastic material are designated here.
AB are made of the same material, but different in the damper dimension.
Yes.
Okay.
But type.
Different viscoelastic material. So AB is the same material.
Yes, but different size.
Same material, but what kind of material? Is there any specific name of the material?
Chang. So this is Chang paper.
Some chemical, I don't know, component or
Types. It says here type less sensitive to temperature and wind. this one, it's a type C is
Yeah,
different.
yeah. Could you go up?
Up.
Could you go up?
Up.
Yeah.
Questions.
Yeah, what kind of rubber? It's a rubber, right?
Yes, I will try to find out what kind of rubber they use. I also found some books that explain about the theory of viscoelastic, but it's kind of long to describe. Yeah, I will find out what kind of damper that viscoelastic rubber they use.
Yeah. Also, the damper for Smith Morrison and the other company, I want to know they are using this material.
I have one question, Sensei. If we find the material, do you prefer to use the damper from Japan, or you want me to use from the Crystal Plus, the properties?
Damper from Japan?
I mean the properties.
Mm-hmm.
Do you prefer me to choose from Japan catalog, or we can just use from Crystal Plus data?
You mean the damper used in the paper?
Yes.
Crystal Plus.
Yes. Or you want from Japanese catalog?
Yeah, I was thinking to do some experiment. So of course, if we do experiment, we must find a damper available in Japan.
Okay.
It's a high damping elastomer material. Well, it's very complicated, but I just want to know everyone same type of damp material or not.
Okay, Sensei.
Yeah, if there's similar type, we can order well in Japan. Yeah.
Okay.
Okay.
Okay, Sensei. That's all.
That's all? I contacted Smith and I am waiting for the answer.
Okay, Sensei.
Yeah, I just request, I mean, if possible to visit the company. And yeah, they will contact us maybe.
Okay, Sensei. Thank you so much.
Yeah. Who is next? Atae-san?
Yes. This is the model.
Okay.
This is columns and the types of columns.
Yeah.
And this is the brochure analysis without CMD.
Yeah.
And this is the value of property CMD for single CMD and for multiple CMD.
Okay.
This is the model. So after analysis, you can see that it is not very effective. It is just 3% Maastricht. In Kobe, Taft, and Tohoku, it is almost not bad, but in El Centro, even it is negative. So I was thinking about that if an structure get damaged, the stiffness decreases, then there has to be another or one or two or many other TMTs to be turned after damage. So there is in stereo output there is after response eigenvalues. You remember it is after El Centro after I mean that T1 after response.
Yeah.
It depends on different earthquakes. So I decided to use this value T1 for Kobe and divided the mass of the top floor to two. 50 control before response and 50% control after response.
Oh, okay.
Yes, and these are the values. The middle is for this to control the second mode, and the upper and the bottom lower side. These values are for this too. One of them for before response one, and one of them for after response. So here a little there is or more better result, but it is not. Yeah, but it is not. I mean, not trustable because I did a pushover analysis by target drift of and I got that a T of 2.7. So based on this T period, I calculated these values for a single TMD. We can see that we get more better results. So it made me suspected that why by reducing the stiffness and by increasing the time period. So I assumed a very large time period of 6 seconds. We can see that the damages or the values are very small. And we can see that the reduction of displacement is very. And even I didn't stop and proceed with a larger period. It is very. It means that it looks very effective, but it is not. I mean that it is not logical. I think this is before TMD with all the connections yielded, but with these values, it is just yielded to 4, 5 connections, and that's all I said. I don't know why it is like maybe something is wrong.
Well, for example, can I want to draw here? So for example, main building, so this is elastic. Natural period is how much second for elastic?
0.6.
0.6?
Yes.
And then it's yielding, and after earthquake, it is a little bit degrading stiffness.
Yes.
So stiffness is I don't know. How much after response?
For Kobe,
1.27, okay. Yeah. Could you change it again? Yeah, okay, 1.27. Okay. So, but second slope, so I'm very during in elastic response, building in second slope. So this stiffness also not zero, but very small, definitely. So if TMD is designed to match second stiffness, it can be, I don't know, for example, this is K0, and second slope, suppose this is 0.1 multiplied K0.
yes,
In this case, natural P is T0, and this is T1 will be square 10 times T0. And if this is 0.01 multiplied by K0, natural period of second slope is square 100
okay.
T0. So I don't know for sure, but well, if you input large X, there is a なんていうのかな、chance building is go enter nonlinear range.
Yes, thank you.
So one TMD might be tuned for elastic stiffness, the elastic period.
Yes.
One T might be tuned for second slope. I think Sawanya-san also did the same idea. But the question is how much stiffness you assume after yielding. So if you over, you can draw this kind of graph, and
Yes.
you can idealize this like a and you can say this is first stiffness and this is second. Yeah, you can draw SASD curve for by pushover. This is only one line.
Is there output gave us that?
Yeah. From stellar output, you can draw capacity curve.
Okay.
Right? And you can somehow assume bilinear. And one TMD is tuned for this slope, another is TMD tuned for second slope. How about this?
Simply when the period increases or decreases, it means that if the period increases, then the stiffness and damping of the TMD also increases, and it is not trustable because of with that much small value of kiss and damping, it is not trustable that
Unit
works.
moving so much. Did you check the how much movement of TMD if you adapt this kind of long period? Maybe very big movement of TMD.
No, not that much. For example, in El Centro, just 44 centimeter.
The 4 centimeter is a what?
44 centimeter of max displacement. It means that
But
max
how about
displacement.
44?
This is the displacement of TMD.
Yeah, I'm talking about displacement of TMD.
So for 4 centimeters, because we have that much space on the roof to install the TMD. But for example, in the acceleration, it is a T-gal and it's not, I think it's maybe.
Well,
It means that,
is not so big.
yeah, that's okay, but it is possible that under El Centro, the TMD just get 80 gal acceleration.
You are talking about 18, this one.
Yes, Sensei.
Oh. So yeah, so TMD is like moving like a isolator.
Yeah, very slowly. The period is very large and
Mm.
it gets a very small value of acceleration. Without TMD, the top floor has an acceleration of 340 gal. But after that, TMD is reduced to about 230, and TMD itself gets 80 gal of acceleration. And I don't know.
Is this result? I mean, you also try many earthquakes.
Yes, it is. It is for Kobe. I didn't gal, but it didn't decrease the acceleration of floor so much.
Did you get the same recency for Lamp-Thomas model?
No, since landmass is linear.
So you didn't do nonlinear Lamp-Thomas.
No, Sensei.
Could you try nonlinear Lamp-Thomas?
It is possible. I don't know.
Only top story is possible. I mean, single TMD is possible for Lamp-Thomas model.
Okay, Sensei.
So what first you do push over for 3D frame, and then you can automatically convert to by still 3D.
Can I open a landmass, Sensei? There is going to single TMD.
Yeah.
How to make it nonlinear to the 7 floors?
ちょっと待ってよ。Could you open through first without TMD?
3D model?
Yeah, 3D model without.
It means frame model, Sensei?
Yeah, frame model.
Okay.
Without TMD. And could you do pushover? Yeah. And could you output? You click this one. Yes. And put this file.
Oh, okay.
Yeah. And could you do analyze? Could you do push? Okay, so this is a nonlinear model for frame model.
Oh,
Then you can put TMD at the top. Maybe you put some floor and some damper element and elastic element. Yeah, yeah,
yes. Okay.
yeah. Could you,
Okay, sensei. It is.
you don't need to column. You don't need to column. Just the damper in the middle. Yeah. It's a random. You must put some rigid floor. First you must option member. And maybe you mix. Okay. Yeah. Yeah. The property. Could you do it again? And which okay, rigid. Okay, fine. Yeah. Okay. Yeah.
Oh, no need. Yeah.
It must be D2. Huh?
Okay.
D1, D2. Okay. This must be D2, right?
Yes. Sorry.
And you must also input weight and height. Could you go down one story? Please make rigid floor here also. But you must check this one. And the seventh floor also, yeah. Not 3D, maybe. そっか。これでもいけるかな。maybe it works. Maybe it works.
Rigid? Okay.
It works. Yeah. I don't know. Could you run? Okay. Could you see? First mode. How about second mode? Okay. Yeah. I can.
Yes, that works. Yes. The movement is okay.
Yeah. So please try this one to compare with frame and to check you got the same result or a similar result or not.
Okay, Sensei. The stiffness of that floor is the same as the stiffness of frame model, or it is?
No, it's not the same. It is frame is a little bit stiffer. It's
Okay.
simplified to linear. So still lump mass model is a little bit, natural period is longer.
Okay, Sensei. I try. If I question, maybe I will take an appointment through email.
Well, Okay.
And that's all.
Okay. Anybody has anything to tell today? 真島、
いや、何もないです。
真島くん、まだ大学いる今。
はい、います。
明日から、
はい。
ちょっと俺の部屋寄ってくれる？
はい、わかりました。
ものがあるので。
はい。
はい、はい。じゃあ、shall we discuss next meeting? Today's 10. Next week. 10 o'clock?
Example 18 since 19, is it okay?
19. Afternoon, I must go outside. 20.
20 is okay.
What time is it? Anytime?
Anytime is fine. Morning?
Morning, 10 o'clock in the morning?
Okay.
Is everyone okay? Yeah, so next control group meeting is 20 and it's 10 o'clock. Okay, so see you. And Zafira-san,
Yes.
if you finish, and of course you must tell me the story.
Okay, sensei.
Please contact me. We can have a meeting and
はい。わかる。
yeah. Okay.
あ、
So,
先生、
はい
少しだけいいですか？
はいはい。
今、Excel 見えますか？
画面、OK、見えます。はい。
振動台に入力した変異と
うん。
計測変異の比較をしてるんですけど、
うん
例えばこの L セントの場合、黒色が計測した変異波形で、
うんうん
赤色が入力波形で、パッと見多分重なってると、
うん
この差を計算しようとしたときに、
うん
計測は 100Hz でやっていて、でも入力は、0秒ごとにやっているので、その入力の刻みと出力の刻みが違うんですね。
うんうんうん
この場合ってどうやって差分を計同じやつだったら引き算して差を出せるんですけど、これってスペクトル書いて合ってればそれでいい。
そうだね。まあ波形でもう合ってるからね。
多分合ってると思うんですけどね。一応確認しようと思ったんですけど、その差を取って、周波数ってことに気がついて。
そうだね。もう波形とスペクトルで合ってるっていうしかないね。
はい、わかりました。
はい。はい。
はい。それだけです。
はい。OK。じゃあ、see you. Bye bye.